Hi, my name is Ben Carver, and today I'll be presenting our paper, WUKONG, a Scalable and Locality-Enhanced Framework for Serverless Parallel Computing. Python has become ubiquitous for its use in data analytics. There are a growing number of Python data analytics libraries reaching maturity, allowing for R and Scala users to utilize the flexibility and performance of Python without sacrificing functionality. For example, Dask is an open source library that automatically parallelizes Python-written data analytics code, including software which uses pandas, NumPy, and SciPy. Dask is capable of parallelizing a workload on a single machine or across an entire cluster. Dask takes advantage of the fact that problems related to big data and data analytics are often inherently parallelizable. These problems can be represented as a directed acyclic graph, or a DAG, where the nodes are short, fine-grained tasks and the edges indicate data dependencies between these tasks. Because data analysts and domain scientists are being faced with larger problems and increased resource demands, they must often deploy large, serverful frameworks to execute their jobs. The task of deploying and configuring these frameworks can be challenging, and furthermore, they can be expensive to run. Serverless computing, a new cloud computing model, is an attractive platform on which we can parallelize these large-scale data analytics applications. Serverless computing enables a new way of building and scaling applications by allowing developers to create applications composed of individual, fine-grained cloud functions. A common example application is one in which a user uploads photos to AWS S3. These uploads trigger the invocation of an AWS Lambda function, which performs some sort of processing on the photographs, perhaps cropping and resizing them. Once the Lambda has finished processing an image, it writes the updated image back to S3. The benefits of serverless computing make the platform a good target for use in developing a parallel execution framework. The first benefit is that serverless computing is cost-effective. Users are charged using a fine-grained, pay-per-use billing model, which ensures that they're only billed for the resources they actually use. This pricing model is particularly attractive for use in a parallel execution framework, as users won't be charged for any downtime in between jobs, nor will they be billed for any startup or teardown time. The second benefit is that serverless computing offers high elasticity. Serverless functions are capable of scaling to hundreds or even thousands of concurrently running instances in seconds. Finally, serverless computing is automatically provisioned and managed by the cloud provider. The cloud provider is responsible for managing the servers on which serverless functions are hosted. Altogether, these benefits make serverless computing a great target platform for developing a parallel execution framework. If designed properly, a serverless execution framework can be highly cost-effective and easy to use while still delivering excellent performance. There are, however, a number of challenges to scaling parallel programs in serverless platforms. The first challenge is that of rapidly scaling to thousands of serverless Lambda functions instantaneously. The chart in the lower left shows the time it takes for Pyren, a state-of-the-art serverless execution framework, to scale to 10,000 concurrently running executors. As you can see, it takes Pyren nearly 2 minutes to scale to 10,000 workers. Ideally, a serverless parallel execution framework could scale more rapidly than this. The second challenge is that of excessive data movement, due to the inherent constraint of serverless platforms in which communication is restricted to outbound-only network connectivity. The chart in the lower right shows the total network I/O performed by NumPyren, a state-of-the-art serverless linear algebra framework, during the execution of a matrix multiplication workload. As you can see, though the input was only 10 gigabytes and the output was just 5 gigabytes, hundreds of gigabytes of data were read and written throughout the workload's execution. This illustrates the excessive data movement that occurs when using serverless computing platforms. Again, this excessive data movement occurs in part because of the platform's restricted, outbound-only network connectivity, and because serverless functions are ephemeral, running for only a short period of time before being reclaimed. The last challenge is that of per-function resource limitations, such as only having 1 or 2 CPU cores and up to 3 gigabytes of main memory per function. These resource limitations result in each individual function performing relatively slowly compared to what is possible using serverful virtual machines, which offer a much wider and more powerful range of hardware options. With all this in mind, naively porting a serverful parallel computing framework to a serverless computing platform won't work. A serverless parallel computing framework may not care about traditional metrics such as load balancing and cluster utilization. As a result, the design of a serverless parallel computing framework must take into account both the benefits and challenges of using serverless computing. We can identify 3 key design goals. The first goal is to accelerate task scheduling. If utilized properly, serverless computing's high elasticity could be leveraged to boost the performance of task scheduling and management. The second goal is to reduce data movement. In order to fully take advantage of the platform, we must develop techniques to mitigate the overhead associated with transferring data over the network, as this can rapidly degrade performance. Finally, our last goal is to improve cost effectiveness. Serverless computing's fine-grained pay-per-use billing model enables the design of a cheap, cost-effective framework that only incurs cost while it's actively doing work. This is where our framework WUKONG comes in. WUKONG is a serverless-oriented, locality-aware parallel computing framework. WUKONG partitions the work of a centralized scheduler across many serverless executors, greatly improving performance. WUKONG's design enables tasks to be scheduled and executed concurrently, reducing resource contention while providing automatic resource elasticity and cost effectiveness. Here, we see a diagram showing WUKONG'S architecture. In order to illustrate how WUKONG addresses the previously identified challenges, we will observe the journey of a typical workload executed on WUKONG. First, the client submits their code to WUKONG's client interface. The user's code is passed through to WUKONG's DAG generator, which generates a DAG that gets sent to the schedule generator. This component performs static scheduling on the DAG, partitioning it into a number of subgraphs. These subgraphs are then assigned to serverless executors that are invoked by WUKONG's scheduler. Once invoked, the serverless executors begin executing and dynamically scheduling the tasks contained within their assigned subgraph. The use of subgraphs here allows the executors to accumulate a local cache of intermediate data, greatly reducing the need to transfer such data back and forth during the workload's execution. In addition, the process of invoking new executors is spread out across the fleet of existing executors, enabling WUKONG to rapidly invoke new functions and scale its pool of workers quickly. The use of a large pool of workers helps to mitigate the relatively modest hardware specs of each individual executor. Workers communicate with the storage manager during workload execution to dynamically schedule tasks and transfer any necessary data. As results are generated, they are sent back to the static scheduler's subscriber process, which transfers these results back to the user. In order to execute jobs efficiently, WUKONG uses two methods of scheduling, known as static and dynamic scheduling. As mentioned, static scheduling involves partitioning the input DAG into a number of subgraphs known as static schedules. These static schedules are then assigned to serverless executors. Executors use dynamic scheduling to enforce data dependencies and cooperatively schedule tasks found in multiple static schedules. The chart on the right shows a simple input DAG and how it would be broken up into two static schedules. Next, we'll walk through a simple example to see how this DAG would be scheduled and executed by WUKONG. First, the user-submitted code will be converted into a DAG. This DAG will be partitioned into the two static schedules, and these two static schedules will be assigned to a unique serverless executor by WUKONG's scheduler. Once invoked, the executors will begin executing tasks contained within their static schedule. Executor 1 will execute tasks A and C, while Executor 2 will execute tasks B and D. Notice that task E is contained within both static schedules. In order to execute task E, the two executors will use dynamic scheduling to cooperatively assign the task to just one of the two executors. If it were decided that Executor 1 would execute task E, then Executor 2 would store any required data in WUKONG's storage cluster so Executor 1 could retrieve it. Here we'll walk through a short example fan-in operation to get a better idea of how this cooperation works. In this case, we have three tasks, task A, B, and C, fanning into task D. Let's assume that Executor 1 is the first to finish, followed by Executor 2, and Executor 3 finishes last. When Executor 1 finishes executing task A, it will increment a counter associated with task D in the intermediate storage. When the value of this counter is equal to the number of dependencies of task D, in this case 3, D will be considered ready to execute. When Executor 2 finishes executing task C, it will also increment task D's dependency counter. Finally, Executor 3 will finish executing task B, and once again increment task D's dependency counter. Since task D will now be considered ready to execute, Executor 3 will become task D and execute it locally. Next, I'll briefly go over a quick example of a fan-out operation in WUKONG. Let's say we have the following DAG with a task A that fans out to three downstream tasks B, C, and D. The executor responsible for executing task A will invoke new functions for two of these downstream tasks. For example, the executor may invoke a new Lambda function for task C. This Lambda function would then be responsible for executing C and any of its downstream tasks. Likewise, Executor 1 may invoke a new executor for task D. In this case, Executor 3 would be responsible for executing task D and any of D's downstream tasks. Executor 1 would then execute B locally, and then become responsible for executing any of its downstream tasks. WUKONG uses two other important optimizations to further increase data locality and improve performance. The first is called task clustering. Task clustering is used to eliminate intermediate data transfer by executing downstream tasks locally within the same executor. The second optimization is known as delayed I/O. We delay performing intermediate data transfer by waiting until all downstream tasks are ready to execute, meaning all of their data dependencies have been resolved. Once they are ready to execute, we perform task clustering on these tasks, eliminating the need to perform the intermediate data transfer. I'll briefly go over two examples to demonstrate how task clustering and delayed I/O work. Consider the diagram on the left. Task A has three downstream tasks B, C, and D. If task A's output was large, it may be desirable to prevent performing any network I/O to transfer A's data to downstream executors. In this case, the executor responsible for executing task A would opt to execute tasks B, C, and D locally rather than invoking new functions to execute them. Delayed I/O is similar to task clustering. Consider the diagram on the right. Task A has two downstream tasks C and D. Task D needs data from task A, task C, and task B in order to execute. Normally, task A would write its data to intermediate storage, and then executors would cooperatively determine who gets to execute task D as the data dependencies resolve. However, since task A's output is large, it is desirable to avoid transferring this data over the network. The executor responsible for task A can decide to not write task A's output to intermediate storage. Instead, it watches and waits for task C and task B to complete. Once this occurs, the executor will execute task D locally, avoiding the network transfer of task A's data. There are several key design takeaways here. WUKONG addresses serverless computing's restricted outbound-only network connectivity and low bandwidth by introducing decentralized scheduling, delayed I/O, and task clustering. These techniques increase data locality, greatly reducing network I/O performed during the job's execution. Less network I/O performed leads to better performance and further leads to increased cost effectiveness. Decentralized scheduling also enables WUKONG to rapidly scale out to thousands of serverless executors in seconds by distributing the task of invoking Lambda functions across the entire pool of existing workers. Next, we'll discuss some results from WUKONG's evaluation. When evaluating WUKONG, we compared the framework against Dask Distributed, a serverful Python data analytics framework, and NumPyRen, a state-of-the-art serverless linear algebra framework. We compare against Dask because WUKONG and Dask share the exact same programming model. WUKONG uses Dask to generate its input tags. We compare against NumPyRen because it's one of the most closely related existing serverless execution frameworks. Our goal when conducting the evaluation was to answer the two following questions. Can a serverless execution framework provide competitive performance against traditional serverful execution frameworks? And also, how does WUKONG's performance compare against related state-of-the-art execution frameworks? This slide shows an overview of our experimental setup. Please refer to the paper for a more detailed explanation. First, we'll look at the results from running tall and skinny QR decomposition on the various frameworks that we tested. This first chart here shows the results for Dask. We used two different configurations of Dask, the first of which consisted of 1,000 2-core workers and was closer to WUKONG's setup as each Dask worker was configured to run like a Lambda function, and another configuration of Dask consisting of 125 16-core workers. This configuration was a more realistic cluster configuration. The 125 worker cluster was significantly more powerful than the 1,000 worker cluster. We believe this is because each individual worker was significantly more powerful and able to complete more work in the 125 worker cluster, and they were also able to build up a larger local cache of data, so there was less network I/O being performed. Next, here are the results for NumPyRen and Dask together. We also used two configurations of NumPyRen. One configuration used S3 for intermediate data storage, which we compared against WUKONG's multi-Redis configuration, as both of these used a scalable intermediate storage. The other configuration of NumPyRen uses a single Redis instance for intermediate storage, and we compare this against the corresponding WUKONG single Redis configuration. We use these two configurations of NumPyRen to try to account for the differences in their storage in order to make our comparison as fair as possible. As you can see, both configurations of Dask outperformed both configurations of NumPyRen for the smaller problem sizes. As the problem size increased, the performance gap between NumPyRen and the 1,000 worker Dask cluster began to decrease. However, once the problem size reached 8.3 million, the Redis version of NumPyRen failed to complete the workload. Likewise, once the problem size reached 33.5 million, the S3 version of NumPyRen also failed to complete the workload. Finally, we see the performance data for WUKONG. WUKONG outperformed NumPyRen by a considerable margin for all problem sizes. WUKONG also outperformed the 1,000 worker Dask cluster for all problem sizes above 131,000. The 125 worker Dask outperformed all of the other frameworks. This chart displays a comparison between the network I/O performed by both Wukong and NumPyRun during the execution of various problem sizes for TSQR. As you can see, Wukong reads and writes considerably less data than NumPyRun, especially in the case of data written, in which Wukong writes several orders of magnitude less data. This graph helps to explain the performance difference we saw in the previous slide and further demonstrates the efficacy of Wukong's locality-enhanced scheduling techniques and optimizations. Finally, these two charts display a CPU usage and monetary cost comparison between the various frameworks that we tested. The chart on the left shows a CPU usage comparison between all of the frameworks. As you can see, Wukong required a small amount of vCPU relative to both configurations of NumPyRun and the configurations of Dask. Wukong was able to complete the workload faster than both configurations of NumPyRun while using a smaller amount of CPU overall. The reason that Wukong did not reach more than 106 vCPUs during the workload's execution is because many of the tasks required only a small amount of work. Wukong rapidly scaled up to execute these tasks and then allowed those executors to be reclaimed by the cloud provider. By the time more tasks are scheduled, the previously invoked executors had completed their work and exited, effectively forming a scheduling pipeline. This result demonstrates Wukong's ability to take advantage of serverless computing's high elasticity and pay-per-use property. The chart on the right shows a comparison between the monetary cost of the various frameworks that we tested. As you can see, Wukong was able to deliver effective cost savings, executing the workload more quickly than both configurations of NumPyRun while costing considerably less money. Additionally, Wukong was able to provide competitive performance against Dask while costing less than both versions. However, Wukong was slower than the most powerful configuration of Dask. Next, we have two charts which help illustrate the impact of Wukong's increased data locality and related optimizations. First, the chart on the left shows the aggregated execution time breakdown with and without task clustering and delay I/O optimizations enabled for singular value decomposition, or SVD, 50K by 50K. As you can see, with the optimizations disabled, Wukong spends an overwhelming majority of its time performing I/O. When the optimizations are enabled, however, task execution becomes the primary activity performed during workload execution. Next, the chart on the right helps to quantify the impact of these optimizations on end-to-end performance. The baseline bar shows the execution time for SVD 50K by 50K, with both optimizations disabled and a single Redis instance used as the intermediate storage component. Switching to a large cluster of Redis instances results in a 20.85% performance improvement. When task clustering is enabled, performance improves by another 48.28%, and finally, enabling delayed I/O results in a 46.21% improvement once again. Overall, Wukong is 4.6 times faster when all optimizations are enabled. Okay, the last thing I want to do here is run a quick sample application on Wukong so you can see what it looks like. So I'm going to start by importing these two required packages. These are for the static scheduler of Wukong. So once I've imported them, I can create this static scheduler object. I'm just passing the host IP address, which is 0000, and it uses port 8786. This is where I have the key value store proxy running, and these are the number of Fargate nodes I want in the storage cluster. This is a bunch of debug information. These are all of the processes used to invoke lambdas from the scheduler. I'm going to create a new client object. Client object is how you submit jobs to Wukong. Next, I'm going to use Dask to generate a random array with the size 128,000 by 100. And we're going to partition it into 10,000 by 100 chunks. We're going to be running SVD. So this operation here sort of generates the SVD operation that we're going to execute. And in order to start and run the job, I type v.compute. There it goes, and it spit back the answer. So all of this, we're invoking executors, and eventually we obtain the result from Redis, and we return the result to the user. So that's what it looks like. In conclusion, Wukong is a scalable, locality-enhanced framework for serverless parallel computing. Wukong can execute jobs up to 68 times faster, reduce network I/O by orders of magnitude, and achieve up to 92.96% tenant-side cost savings compared to the state-of-the-art. Wukong is easy to use, requiring minimal configuration, and provides competitive performance against comparably priced serverful frameworks. So thank you everybody for watching. If you are interested, the source code for Wukong is available at this URL. Feel free to download it and test it, see if you can do anything interesting with it. And I also listed my emails here if you want to contact me for further questions. Thank you.